the planets to line up the right way back again, and then take at least another 6 months back. So at a minimum, you're looking at a 2.5, 3-year mission. And how the hell do you keep people alive for that long? We don't have the technology to do that right now. But then on the other hand, if you want to look at short time scale missions to keep the life support technology within the level that we can do right now, say like 6 months is a typical ISS expedition, well, then you need much more efficient propulsion to do that. You need something that can generate relatively high amounts of thrust and still have relatively high specific impulse. And we haven't figured out really exactly how to do that yet either. And there are people that have ideas for how we can do that, but we haven't really invested in the kind of technology R&D for quite some time to actually test some of those concepts and prove them out. So, for example, one propulsion concept that's out there is that we would use the Orion drive that was theorized back in the 50s, where essentially you'd have a spaceship connected to a pusher plate, and you would eject essentially small nuclear charges out the back, detonate them a certain distance away, and that would push the spaceship along to its destination. The advantages are that it's actually surprisingly very efficient. You get very high specific impulse, and you can also generate high thrust with that method. The problem is you are detonating small nuclear weapons behind you all the way out there, and you have to lift all that up in orbit in the first place. You could feasibly fire them off to push you up into orbit, and there are people that actually looked at that. But then that runs into the problem that you're detonating nukes all the way behind you up into orbit. So that obviously never gained a lot of traction. It was more of a theoretical exercise. There are also people that have looked at various schemes for nuclear thermal propulsion. I know that was discussed in the previous talk. So you could, there are a number of different ways you can do that with a solid core, a liquid core, a gas core, and you'd have exhaust of varying degrees of radioactivity depending on how you build that. For example, there's one propulsion concept called the nuclear light bulb. It contains uranium hexafluoride in a gaseous mixture, essentially in a quartz cone, that you use the radiation from the gaseous uranium to superheat hydrogen fuel that you shoot out the back. Theoretically, it's very high efficiency, but then you have to carry huge freaking tanks of hydrogen to do that. So that gets you into design problems like, okay, well, how do you build a vehicle that's big enough to carry all of that hydrogen, transport all of that mass, keep it from boiling off, and so on and so forth. And then there's a concept that Robert Zubrin came up with, they call the nuclear saltwater rocket. And that's an interesting idea in that you could generate fairly high amounts of thrust by having a high mass flow rate, but then that raises the question, okay, how do you get all of that water to fuel the rocket? And so as you go through all the trades and look at that, it starts to look like you can't really do high efficiency, high thrust propulsion until you figure out how to do something like fusion, which everybody says, oh, if we can figure out fusion, then it gives us cheap energy and you can build fusion rockets, and that's easy. But also everybody says fusion is 20 years away from the last time you talked to the scientist working on it. So that leaves you wondering, okay, what can we do right here and right now? And I actually found a study paper done out of Glenn that they looked at an old concept called a fission fragment reactor. And
fission fragment reactor.
And the old concept is that you'd essentially have small or relatively small disks of fissioning material that you could rotate to control the moderation and eject the mass out the back to generate thrust. Well, these guys at Lynn figured out that with modern magnetic containment technology that already exists, you could essentially suspend a kind of a dusty cloud of uranium particles such that the relative surface area is large enough that you can thermally control the reaction just with the magnetic field. And the electron stream you could direct into collectors to generate power, and then you eject the heavy uranium ions out the back to generate thrust. And they're able to come up with a 350 megawatt reactor design that could transport a large unmanned survey vehicle out to the gravitational lens outside of our solar system in 3 years. And if you launched enough uranium fuel, it is theoretically possible that you could generate a high enough mass flow rate that you could do what are called minimum time trajectories to Mars. And this was a concept that was looked at back in it was '54. Essentially, the idea is that if you have constant acceleration out to and deceleration into your target location, you can actually largely pick when you want to leave. Obviously, the closer you are, the less fuel you have to burn, and the shorter your trajectory is. But by doing this constant acceleration deceleration, you can dramatically shorten your time scales, and you don't even have to necessarily fly on a traditional Hohmann trajectory like what you have to do with chemical propulsion. And so with a fission fragment reactor that has a specific impulse of about 1 million, and enough, essentially, if the calculations I did were correct, you could launch the mass of the reactor, its fuel, and the habitat mass-wise on one Ares 5 launch. Volumetrically, you probably have to break it up into 2 components, just because you're not going to be able to fit all of it underneath the payload shroud. But mass-wise, you could actually put it all up in a couple of launches fairly easily. And on a 1G minimum time trajectory, it would only take 4 days to get to Mars, and you can reduce your fuel consumption by about 1/10 if you go on a 16-day 0.1G minimum time trajectory.
Are you able to draw any of this out? Is there like a diagram you have? Or like, I'm just curious, if there isn't, then there isn't, but I'm just curious, like, visually to be able to see, like, because this is obviously something you come up with, right, based on other people's research?
Yeah, essentially, for the paper that I did for that class,
yeah.
I looked at, okay, what would it take to be able to do manned missions to Mars on time scales within the life support technology that we have today.
So you're saying we can get there in 4 days?
If you build, essentially, if you build a nuclear rocket with high enough specific impulse and mass flow rate, you could do that.
Could I ask, just for a number out of your background, what number would you recommend for just a preliminary first-order assessment in terms of newtons and thrust for that particular purpose, newtons and ISP, just 2 numbers perhaps? And I'm going to contribute, but I just need to know the numbers.
Yeah.
If you just wanted to do it according to your mission profile.
Let's see. Let me see if I have the paper with me.
Around Mars in 80 days? No.
That's too much that writer who read the lesson on screw-ups lately.
Are you really having fun? Wait, photo op. I mean, taking a photo op. There we go.
I've already tweeted him and Caleb talking about Pokemon.
No. We've got the Mars Sojourner. We've got the Mars Sojourner getting ready for its first wheels, wheels in motion. So I guess.
Awesome.
I've always been to my tower and think
I guess NASA administrators are looking at this tweet, thing, and they says, "What hath gone wrong?"
They're probably saying maybe we should.
So, I'm sorry, I forgot your name.
Justin.
Justin, do your calculations include slowing down once you get to Mars?
Yes, you do a 1G constant burn out, turn the vehicle around, and then decelerate in.
Constant G.
Yes.
Mm.
I'm pulling it up right now.
No, I mean, it's okay. But let's not stop the flow here. I mean, Justin, I'm just going to ask you, if you had the ability to have a disposable propulsion payload, which you basically, for whatever technology you use, just simply for the extended burn phase, just fire it, and it basically consumes itself, or consumes as much as possible, and then discard it. And if I actually gave you two of these payloads, one for the return mission, one for the forward mission, but the fact is that if you have a orbit out to Mars, a transfer orbit out to Mars, if you just let it go, it will actually come back after a while. It'll be the Mars cycler approach.
Right.
You don't really need to slow down as long as you have Earth to Mars cycler loop and another Mars to Mars cycler loop. So the Mars cycler will just keep on accelerating over time. So initially, the first mission, orbit would be at relatively slow speeds.
Right.
But in the subsequent orbits, it will actually start to accelerate because it will pick up the speed due to the gravity slingshot around the sun, or Earth for the matter of fact.
But let's see, for the 1G trajectory, it's an initial mass at low Earth orbit of 160,600 kilograms, including a departure fuel mass of about 33,000 kilograms.
And the uranium gas fuel?
Yes. And let's see.
I mean, my question is specific because I can contribute something, but in terms of newtons of thrust, a maximum number, is it 100 newtons, 200 newtons, 1,000 newtons? What scale are we talking about that we require that propulsion module to produce?
I'd have to. I was just
Don't worry,
looking at the
we're
paper.
not
I'd have to pull out. I left my calculation.
I was just going to say,
Well, it's
I was
at
just going to
least
say,
33,000
Yeah.
ton,
Yeah.
right?
because that's the weight of propellant.
Yeah.
If nothing else, it's 33,000
Right.
ton.
I was just going to say that I recently wrote,
Megan, you.
a little add-on to Dr. Kada's paper, where I said, and boldly, without any justification whatsoever, initially, this is just a concept. We'll have to develop it, think about it thoroughly. If we had the ability to have a solid metal propellant, which is in our lab we have, it's a thruster which takes up the DC 28 volt electricity at certain current, and basically creates a plasma from the anode and the cathode, uniformly erosion. But if we stacked the thrusters into big arrays, each little thruster of 6 centimeters can operate for 2 years, producing 0.2 to 0.6 millinewton thrust. So we basically try to scale it up both horizontally, vertically, and basically in depth. But if we followed that model and we created a big-ass version of it, right, Mars or bust, but we basically had a propulsion, payload, which would just be a stack of maybe hundreds of thousands of little thrusters with only solid metal propellant. Current generation titanium, next generation who knows what. I theorize that we should be able to give you incredible amounts of ISP because it's using magnetically channeled plasma.
Yeah, actually, I saw one of the proposals that we've seen to do a propulsion technology test bed on the station is, I think this was another proposal out of Glenn, something that they called a quantum vacuum thruster that takes advantage of the Coulomb effect. And this, the Dusty fission fragment reactor design has an ISP of about 1.5 million. So that's about 10 to the 6 ISP. The quantum vacuum thruster ISP was 10 to the 12. And it was effectively propellantless because it relies on quantum fluctuations.
The Casimir effect?
Yeah, sorry, yes, the Casimir effect.
Not the cool.
Glenn has seriously proposed that?
Yes.
That's interesting.
And they were talking about essentially something similar, that you could build essentially banks of these thrusters to scale it up to generate.
Yeah, you would only need to fire
thrust
it pretty much, over a certain amount of time,
Yeah.
consume all the propellant, and disengage the entire frame.
Yeah.
So on the return journey, you're not really hauling dead weight. But I'm just curious if you could give the numbers, maybe publish a corollary to your paper, that if we were to do an 80-day loop, or even less duration mission, we would need to have a number. I mean, so work backwards from the solution. The necessity is the mother of invention. You
Right.
need to fit in 80 days. I don't care how you do it, as long as you can fit in 80 days. If you've got a chemical rocket, you're not going to do it in 80
Right.
days.
And so for the paper I did for that class, that's what I did is I specified a profile for a nominal 6-day mission, and then based on the performance capabilities of the fission fragment rocket, I backed out essentially how much mass you need to carry for the habitat, life support systems, crew consumables, the weight of the crew and all of their equipment, any robotics that they would carry with them to do telerobotic surveys of Mars, all that, and then how much fuel they would need to get out there, how much fuel they would need to get back, and backed it out, like you said, essentially working back from the solution. And so to do constant 1G burn, it would take about 140,000 kilograms. And then if you were willing to go a little bit slower and do a 0.1G minimum time trajectory, it would take 16 days to go out, 16 days to come back, and then it reduces your initial mass at low Earth orbit to 98,000 kilograms. So you only use 22.8% as much fuel if you're willing to stretch out the time it takes to get there a little bit.
So have you thought much about the idea of trying to use this encounter to chase a near-Earth object rather than Mars?
Right, and the goal of the paper was, the assignment for the class was to design a Mars exploration vehicle,
Mm-hmm.
but it was written in the assignment that even though the goal should be to get a crew safely back out into Mars, we were asked to think about other flexible path kind of missions. And I think if you're using a propulsion system that has that kind of inherent efficiency, and you design it and you design the structure in a modular fashion that essentially you can stick on the front end whatever mission module you need, whether to go to an asteroid, go to Phobos and Deimos, go to a comet.
Tug, for example.
Right.
Yeah. See, because from just speaking practically, maybe just even though we're talking about new technology, the practicality of investing the kind of money it's going to take to send humans anywhere is going to necessitate the limitation of the number of miracles you need in order to make that happen.
Right.
Right? And so
You can have some of my miracles.
yeah.
Well,
Well, I mean, the reality is you got to push all that stuff out to Mars, and then you got to land them, right? And just getting a robotic probe on the surface of Mars is very nearly a miracle these days. So the idea of going out to a NEO with this propulsion technology, rendezvousing with a NEO is also challenging, but I would submit it's not as challenging as landing on the surface
Well,
of Mars.
and for the purposes of that class assignment, I actually punted on the landing and essentially set them up to carry equipment for doing telerobotic surveys of the Martian surface to essentially
From orbit.
to essentially look for places where you could build a landing site, establish a base camp. And I actually looked at some of the research that they did in the Apollo Applications Project on small lunar flyers, and the designs that they came up with for the Apollo Applications Project are actually almost exactly what you would need to have a small manned excursion vehicle to get the crew out to, say, the surface of Phobos and Deimos, and perhaps do survey work on maybe building a base camp there,
Right.
and get the crew back pretty safely. It really doesn't take a whole lot of fuel to get there and get back from a vehicle in Martian orbit.
Well, it sounds like you thought that through pretty carefully, because the idea is to not bite off more than you can chew in
Right.
the proposed mission, and if the objective is, I mean, obviously there's a spaceflight objective, but if the miracle objective is to prove out the technology of the propulsion, then you don't want to get that confused
Right.
with another miracle needed to keep humans safe while they go through the 7 minutes of terror.
Right.
So the
And that was
that's smart.
And that was the idea behind the configuration that I came up with for the crew section, is that the propulsion itself would be the revolutionary technology.
Mhm.
The crew habitat is based on TransHab, and I actually did the research into all of the radiation analysis that they did on the TransHab materials, and how they showed that while there's not a whole hell of a lot you can do about galactic cosmic radiation, because people probably can't live inside of a 10 Tesla field, the composite materials inside in the TransHab are actually they found were actually sufficient to keep radiation levels inside such a habitat at acceptable levels during the intensity seen in the solar storms in the late 1970s. They use that as a baseline. And there have actually been some studies that have shown that GCRs are actually significantly reduced during periods of high solar activity. So it might make more sense to actually build a TransHab style habitat, design your water bladder for your crew needs, and an annulus inside the habitat, and fly your crew during periods of increased solar activity, because you can shield them against solar radiation with existing technology, and then use the sun itself to protect the crew against increased galactic cosmic radiation.
But your biggest advantage there is the speediness of the flight. If you're about
Right.
in and out in 16 days, a lot of those issues you don't even have to really address all that much.
Right.
The other thing is that Bigelow took the TransHab work and took it one step further. He might be better off just buying an off-the-shelf component from Mr. Bigelow for 1/10 the price it would take it to develop.
For the modules for the crew had, essentially
Two
the actual
BA330s and you're
habitat
done.
is something you could conceivably buy off the shelf. I had it attached to essentially like a node module based on what we built for the space station, so that you could have, say, Cygnus carry up your cargo for your internal systems, and fly the crew up there on a Dragonflight if you wanted to, and then essentially had an airlock module attached to it, a cupola module attached to it, and then out on the front, essentially an operations truss where you could attach robotic landers, the excursion vehicles, things like that.
Good.
You a NASA employee?
When I was an intern, I was, but now I'm a NASA contractor.
NASA, okay. And who are you affiliated with?
I work for SAIC.
Okay, SAIC. Just one because I'm going through a policy program, space policy at GW. One of the things that, because I was in that last session that was focused on propulsion. We all think back to what NASA had to go through to get Cassini approved for launch. Some of these things I'm hearing are just politically, they're non-starters. I think maybe what you might want to try and think about is trying to find someone's problem to solve. For example, the ISS has propellant consumption requirements for altitude maintenance, and now they're like, okay, we can seriously consider a Bessemer engine to reduce that.
We'll get food, I'll be back.
Cyclic cost, right? Maybe you can find some sort of mission profile where you can take a baby step. Simply just try and think about maybe some sort of electric-enabled thruster technology. So Shamudra mentioned that GW has a very power-efficient, very simple vacuum arc thruster. There are other propulsion concepts out there that just need electric input. Maybe the baby step here politically that American culture and the space establishment can handle within the current budget profile i.e. cheap, is just simply linking an RTG to an electric thruster of some sort. None of this electric or nuclear thermal, none of this stuff with fission products.
RTGs are acceptable universally,
Right.
but if you
Almost.
if you had a nanosatellite, a nano spacecraft, forget the satellite part, nano spacecraft with a EP, electric propulsion, and RTG to power it, optional solar panels for backup,
Yeah.
and you allow 2 years to design, build, fabricate, test and everything.
Mhm.
As an experimental mission, it could cheaply go out to Mars and back.
Yeah. It's
Beep, beep, beep,
Awesome.
beep, 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 and that's it.
mhm.
Sort of the Apollo 8 version to Mars.
I'm not familiar with that term because I didn't grow up here, but I'm just going to point out that, of course, I'll wave the AMSAT flag here, but AMSAT,
Yeah.
being a pioneering organization, wanted to fly to Mars a long time, the Phase 5D mission plan. Forget that. Current generation of aerospace engineers have enough talent to look at all the building blocks of the whole problem
Mhm.
and on their own come up with a National Science Foundation or NASA, combined grant or some other US whatever supported or even private supported program, as long as they can get to LEO to start the departure
Mhm.
towards, say, deep space.
Kind of like what the Planetary Society did with the solar sail.
Could be, that's a good example. I'm not familiar with everything, about what the policy implications are. But if the policy leadership could be convinced that we just need to, what is the term, Kirk, just a proof of concept?
Existence proof is what,
Right.
when there's enabling technology that's already
Yeah, we
there.
just need to prove it. I mean, it can't be tested in low Earth orbit because there's no deep space, there's no long duration mission profile that fits in the low Earth orbit. You can't run a electric propulsion drive over a large amount of time because you just don't have enough space,
Right.
to do anything. But we could swing around the moon.
Yeah.
But if we're swinging around the moon, we're coming back and picking up velocity on the gravity well. So why don't we just simply take a left turn, first start to the left and straight until morning.
Yeah.
I mean, it's the trademark that we need to put on our license plates, right? Get some money for that, trademarking and all that. But I'm just saying that will actually fund a very good technology demonstration program. Nobody will complain if it is just a demonstration program that will just, break the ice, so to speak. I'm just proposing. You've already got the math, so you just need to get the numbers.
Yeah, you had a school assignment, I know, and so you had this mission profile that you had to try and build an architecture for. But if you want to take, now you're in the corporate world, you want to try and make something happen within the political and cultural reality. The thing that hasn't been demonstrated yet, and somebody correct me if I'm wrong, is nobody's actually taken an RTG and made it into a thruster of some sort.
Well, we've looked at it.
You've looked at it,
I
ad
actually run the
nauseam.
division that's responsible for it.
Oh, no.
Okay, so this
Oh, no, you're the wrong person for this.
I am. You probably don't want to hear my opinion.
Realist, we need the realists.
And the opinion is?
So beyond Mars, if you want to do an electric propulsion system, you have to go nuke, and so maybe the baby step to get everybody comfortable, it's called expanding the flight envelope, right? Right. So take that analogy and put it into your context. That little baby step is actually having the RTG just do more than housekeeping. It's actually direct current for whatever thruster is on.
A thruster typically takes 20 to 30 volts DC, but it has a charging device, some kind of inductive storage, which charges up and then it's discharged within a nanosecond, microsecond, millisecond, what have you.
So your thruster is pulsed?
Yeah, it's a pulse. All thrusters are pretty. So electric propulsion is.
And at what frequency?
You could actually. The current lab version that you can see, if we wanted to walk over there, is operating between either 1 hertz, lower end 1 hertz to 10 hertz maximum. That's the capability of the controller that has been designed. The only problem with the thruster as it's on the bench right now, not the bench, the vacuum chamber, is that the junction heats up and or cathode, the breakdown actually cannot happen if the junction heats up. But if certain other materials were to be used, that for that, the separator film between that or the cathode, yes, then that sort of thing should be able to be fired more rapidly. But instead of firing more rapidly, what the proposal I have come up with, and that's the future, development, of course, is that adding stacks of similar thrusters and firing them
Well,
in
phase.
in a cylindrical manner, 12-cylinder.
How much power does your current test bed consume?
Dr. Kedar has measured it, and I'm helping him design the most accurate thrust measurement sensor, but in the absence of that accurate sensor, the core measurements are 0.2 variable to 0.6. Why it's variable, and why we call it a variable plasma microtester, is that its use of magnetic channels, basically for some odd reason, which he can't, it actually accelerates the plasma.
It sounds almost like a smaller scale version of what Franklin's doing with Vasmer.
So it's 0.2, 0.6
Millinewtons.
millinewton
Yes.
output.
And because the whole thing is about
And how much power does it consume, electrical power?
1 watt per pulse.
1 watt.
1 joule
Yeah.
per pulse, actually.
The difference between Cameron Chang Diaz's architecture and GWU's is that Diaz has a working fluid,
Right.
and he's resolved the cathode erosion problem, whereas your guys is solid. It's just a piece of tungsten sleeve.
Right.
But I think the overall point that I want to make is that I think programmatically, if you want to try and build consensus and endorsement within SAIC, and then get maybe DoD or NASA to try and do something with this.
Well,
is to
this
try
isn't necessarily something I'm doing for it. I'm actually in a new master's program at the University of Houston right now called Human Space Exploration Sciences, and that's what that was for. And so mainly I just want to get people talking about the idea that if we can actually start talking about and thinking about new and more innovative ways of doing propulsion, we can actually use existing hardware that was developed for the space station and the shuttle and Mir and other programs to keep crews and systems operating on timescales that we're more comfortable with if we're willing to make that kind of investment in propulsion development. And so as a systems engineer and as a proponent of exploration, I wouldn't necessarily say that I'm wedded to any one particular propulsion architecture. What I'm interested in is having an open and honest investigation into what really works and what will enable us to do that. So I agree. It's like if we start looking into the problem and we decide that for whatever reason, straight up nuclear propulsion is politically untenable, people aren't going to go for it, then I agree. I think the answer is to figure out how we can develop electric propulsion systems that have the efficiency that we need to do it. So I know that when I worked in Franklin's lab, they were working on some of the trajectories, and they found that you could get to Mars on I think it was a 300 megawatt Vasmer in 42 days. And yeah, that's not as good as say 4 days or 16 days, but that still starts putting you in the range of the kind of life support technologies that we have existing today.
So are you satisfied with doing conceptual studies that build a case for a human space flight scenario, or are you interested in some sort of way to show some real flight experience at a smaller scale using some compromises that I pointed out?
I would say that just me personally, I have no personal objections to making compromises to actually start getting out there and doing the research and developing the experience base.
Because I think politically, from what I understand, is that TRL speak, right?
Mm-hmm.
I don't know if everybody in the room understands the acronym or not, but technology readiness levels. If you could take that very simple step of just having the electricity source become an RTG, for example,
Mm-hmm.
and mature that through 7 or 8, and help somebody's science mission get somewhere. Right. Then you take that experience and go to the policy and decision makers and say, okay, the time is right. This is Obama version 2. It's 6 years from now, and the president's ready to commit to some sort of maybe near neo object kind of thing. You would be in a position to offer that technology. So you're thinking very strategically here, and you're thinking on
Right.
scales of years. as opposed to other people, other advocates that I see, which they want to reach for the end game first
Right.
and try and secure funding, et cetera. And that just doesn't work in our space program. I don't think anyway.
Yeah, I think a big problem that we run into is we do try to bite off more than we can chew. I think that was something we ran into with the Constellation program, and it came back to bite us.
Price tag was a little steep on it.
Yeah. Where, I mean, if you, especially from policy perspective, if you look at the vision for space exploration, and you look at what the Aldrich Commission recommended, they both explicitly told NASA, do not go build new boosters if there's existing hardware that can do the job. And instead of taking that guidance, we went and said, oh, we gotta build all these brand new boosters and spend all this money on it. And now here we are 6 years down the road and about $10 billion spent and nothing's flying yet. So I agree that's something that, regardless of what architecture or what path we pick, that's something that has to be kept in mind at strategic levels. How do you make the program sustainable and survivable? How do you build it in such a way that you can actually give something back at the end once you spend the money and say, yes, this had value added back to the community.
Yeah, maybe even a simpler step would be if you could find a flagship mission that you get them willing to have a redundant thruster.
Yeah.
Right. They won't put you into the critical path. They'll rely on hydrazine or whatever, but you basically get concurrence to allow a prototype thruster to be put on as a secondary payload, and that would even be a smaller baby step.
And another thing I've been hearing is that Dr. Braun in the Dr. Bobby Braun, the new chief technologist, he gave us a presentation at JSC that showed how he's got things pretty much lined up into 3 areas, essentially like white papers and overview studies, then lab work to elevate TRL, and then a handful of actual flight investigations. And from what I've been hearing, his office is actually very interested in looking at revolutionary propulsion technologies that could dramatically shorten mission timescales. So that's also another opportunity.
Yeah, I don't know what the room thinks. I've been through 2 sessions now on nukes this morning, and to me, you know what? Maybe the public perception issue is that if somehow the public figures out that fission products aren't coming out the end of a nozzle and just generating electricity, that's more palatable than stuff spewing out.
I agree.
It's the R in RTG that the public has.
Radioactive versus radioisotope?
That's their main concern.
Rename
Is
it.
that they're not going to think, oh, this is a generator.
Well,
But they are going to focus on R radioactive.
Well, the thing is, I think there are some opportunities for synergy there, because I think it's becoming an increasingly more palatable idea here in the U.S. that we need to start building ground-based nuclear reactors to meet our energy needs, so that we can start taking some serious steps to reduce foreign fuel imports, for example.
Without diverting from the actual mission of space, I mean, that's terrestrial, issues.
I'm getting to that, though.
I have a relevant question for you. You're going to be flying a spacecraft at high velocity, relative to planetary motion, in and out. Have you given any thought to the guidance, navigation, control, and the communication requirements during the mission profile? And if you haven't, then I'd like to say, perhaps we could talk offline about my upcoming work, which would help in establishing gigabit class or more than gigabit class communication across Earth and Mars.
Yeah, I know there are people that are working on concepts for that in the space communications area at NASA Glenn. And so for the purposes of the paper that I wrote, I essentially assumed that they had already established that communications network. and that the mission that I was writing was piggybacking off of that.
Gigabit class communication in deep space?
He just made the
Yeah.
assumption that it was there.
How about hundreds of kilobits on a moving target from Earth-based systems?
Oh, that didn't sort of figure that one out.
BitSup's got nothing to do with it. He's just the upper layer guy. I mean, you've got to keep your foresight on station, on target, and you've got to track it, and you've got to wait for the whole thing to come back to you.
Yeah.
So I'm working on a completely separate infrastructure proposal, which would actually establish persistent, a network of persistent interplanetary relay.
Mm-hmm.
Spacecrafts in heliocentric orbit, so orbiting the sun.
Mm-hmm.
But that would allow us to have pretty much a Earth to Mars, network where you can just simply, pick up the telephone and have a conversation in quasi-real time, if you wish.
Yeah, like I said, there are people at NASA Glenn that have very similar ideas, and they're looking at using the station as a test bed for some of those technologies.
Wow.
And so like I said, for the purpose of the paper, I assume that their work was available to take advantage of.
Okay.
So there's a chicken and egg
Yeah.
problem with all of that sort of thing.
Yeah.
And the chicken and egg, and
I keep raining on the parades here.
No,
the chicken and egg problem is that, and we saw this at the moon too, why put up a communications relay if the humans aren't going to be there? But then you're going to want the relay if the humans are going. And so we saw this kind of just constant, not sure I need that. And then the human spaceflight community says, well, I can find ways to live without the expense of having to put up the infrastructure
right.
for communication.
A long time ago, the Phoenicians, et al., in antiquity, they didn't know where they were going. They just basically went from coast to coast to coast.
Mm-hmm.
Eventually, it morphed into more of a formal sea lane navigation system. Fast forward a couple thousand years.
Lunch is ready.
Oh, right, great. Then I'm done.
I always finish the sentence.
Fast forward a couple of thousand years, every map that has ever been created has been to exploit wealth or reach out and conquer more resources. And without those maps, without those waypoints or guides or markers, humans couldn't have gone anywhere.
I agree.
And what's happening is that in the aviation industry, we've just switched off LORAN, the radar system, but we've switched off because we've gone to a satellite-based navigation grid. And in the space industry, though I completely agree with you that most space missions are pretty much ground, controlled, ground tracked and everything, but there's a dual advantage. There's a dual advantage to consider a navigation system for deep space missions, because each of those relay points theoretically could be potential lifeboats, just in case the mission actually develops a problem en route. I mean, that is probably a selling point that is not considered, other than just simply saying it's just a relay navigation point. If we had a store of emergency parts, like a wrench or something like that, okay, or just emergency rations, so that at least if they get stuck, they can, push themselves onto the next, the lifeboat. And that is the key reason why we have lighthouses over the coasts, and why the lighthouses were the original point where the LORAN network was set up. So that at least the LORAN was not for figuring out where you are, but how close you are to safety.
Right.
So depots. Right. Sorry?
Yeah, essentially.
Depots. Yeah. So I'm just saying that the perception, what is the idea has to be sold. Can we risk our, astronauts' lives on some bureaucrat saying that no need for a communication network, we'll just do everything on ground-based.
But I do like
I'm just
what you were getting at. I do think there are opportunities there, because I think nuclear energy is becoming less and less of a dirty word if it's used for power generation. And so I think
sneaking it in, if you will, under the radar is, we just need to create electricity for our thruster.
Right, and so I think there are actually opportunities
propulsion
there
electricity.
that, I think if NASA and DOE work together on developing a relatively lightweight, passively safe nuclear power generation system that could be just as easily put on a spaceship as be used to power a city, I think that might have a transformative effect on the discussion.
Again,
I think for the power levels you're talking about, by the way, you're not talking about RTGs anymore.
No.
Yeah.
An RTG is powered by plutonium-238, and an RTG is at its best 8%
Right.
efficient.
Right.
The best we're getting out of them today, out of the MMRTG, is 110 watts or so for a whole unit. So
And you're going to need more
that's
than
the
that for
scale.
something like a VASM.
Yeah, so we just had a study run cooperatively between Glenn and the Department of Energy on what's the smallest you could build a nuclear reactor power system. And the starting point of that is at the at the 10 kilowatt level of power output, right? And that uses Stirling engines to create the electricity that's taken from the nuclear power. But it's the whole thing with the sticker that says it's a problem that at some point we're going to need so much power that we are going to need these nuclear generators in space, and we are going to have to overcome the stigma, which was the last session. So, pretty amazing. Yeah.
Does nuclear power freak you guys out? Is that a word? No? You're cool with nuclear power?
Yeah.
Just curious.
Can I ask you which school you're attending? Is it UMD here?
No, I'm from Houston, so
Oh, okay.
I'm
You teach?
Oh, really?
I'm actually University of my previous teacher was from Texas.
I've heard very good things about this. I actually came to the US 5 years ago and had to like restart. Mostly it's been
Is Holy Mother one of your?
Yes, and I have a class
space studies
program.
Help yourself. Or to build a set of fiber optic.
Well, they're
Made by a truck.
pipe
cleaners aren't the most stable platform anything.
Reached out
No,
to
Michael said he
JPL.
fidgets all the time and likes to have
But they
things.
had
I have a stress ball that I like to play with, so this is like awesome for today.
I've been playing with,
We can help you with your own.
do you know Thinking Putty, Silly Putty?
Yeah.
So I have a wad of that stuff and I'm just
That's
squeezing to
awesome.
death at my
Yeah.
desk lately.